So I will be proving the following formula. So the gradient dotted with the gradient cross f, and this is equal to 0. So the way this is done is just by basic expansion of what we have on the side. So we would usually always deal with the brackets first. So we know that the gradient named num blah, I think it's called something like that. Nambla is defined as the column vector partial with respect to partial x and so on to partial n xn. So that's how the gradient is defined, and we'll expand this formula according to that. So looking at this would be called the curl of a function. In this case, multivariable functions only curl. So we look at the curl of f first, given by curl of f equals 2. Then taking that, it would be gradient, partial gradient x1, partial gradient x2, partial gradient x3. One thing I want to point out here is that for this we're gonna be proving under these conditions. So f will be mapping from R3 to R small f in this case. Now small f is not going to be used here obviously because it's not defined in the formula, but there's another part of this system that's similar to this, but for now the small f being a scalar valued function, we're not going to really worry about that for now. So what we are going to worry about is that capital F, which is a vector valued function, is going to map from R3 to R3. What this does for us is it allows us to use cross product notation. So okay, I'm getting a bit ahead of myself here, but what we would do is, looking at f is, so okay, let me take that out. F basically looks like x1, x2, x3 being equal to also a column vector. Could be a row vector, but it's more common to have it as a column vector. So f1, f2, f3, denoting the function value when x1 is evaluated and x2 and x3 are kept constant, and same for f2 and f3. So that's that. I just wanted to clarify that before we move on. So this is now the gradient. The curl of f is the gradient with a cross product of f. So it's f1, f2, f3. Okay, because this is defined as gradient cross product f. Okay, sorry about that, so you can't see. Okay, so now looking at this, it's not really easy to see how a cross product would be done, but if you sort of take a transpose, not in an actual sense, but saying that is an abuse of notation, but mentally you just would take a transpose. So that would be, now remember when you're taking the cross product, you have to take the determinant of the 3 by 3 matrix. That's why this definition is so important. So I partial x1 for f1, j partial for x2, f2, k partial x3 for f3. Can you see I've just taken the transpose there, Now how this is evaluated is you would actually find I think it's called the minor of this part by cancelling out its row and its column. For j you would do the same, cancelling out its column and then its row and so on. So that is actually going to be, we would put this in a column vector, because the cross product always gives out another vector. So cancelling out this and this, the cross product is going to be going in this direction. So I don't know if you can see that, but it's going to go in that direction. So it'll be partial x3 f2 minus partial for x2 f3. Can you see it's going to go there, subtracting here? That's just the determinant. Now for j, we're going to go in the same direction, going that way. So it's partial x3 f1 minus partial x1 f3, and then obviously the same. So it's going to be partial x3 f1 minus so it's going that way, partial x1 f3. Makes sense? Something doesn't make sense here, because we have f3. Something has to be wrong. So let's see what is wrong. So we have to cancel this one. So we automatically know f3 shouldn't be here, but it can be in there and it can be in there. So something's wrong here. When we've taken that out, it's going to be f2, so it's not f3. Okay, that's our curl. So that curl. Then we would take the dot product with us. So that would be x1, x2, x3, like that, dotted with what we have there. So it's x partial x3 f2 minus partial x delta, not delta, but you know, x2 f3 x3 f1 minus x2. I hope you don't mistake these for 2's, because it can seem pretty easy to do that. That's supposed to be f1 f3. Now guys, this is just normal copying, nothing really special here. Okay, now we always know that the dot product gives a scalar, so it would basically just be that times that, that times that, that times that. So it becomes x1 x3 f2. Now this is the same as saying taking the partial derivative with respect to x3 of f2. So you would have a multivariable function like what I was explaining here when I erased this stuff. This f2 would be the function value evaluated with f2 keeping x1 and x3 constant. So It's the same idea. When you multiply, this is also again an abuse of notation, but when you multiply by the derivative, it's basically taking the derivative of f2 with respect to x3. So, okay, continuing the copying, 3 there. Now it's going to be plus because that's how the dot product works. X2 times del, this is called del, actually it's a Greek letter, f1 minus x1 plus del x3 or partial, whatever, x3 f1 minus x1 f2. Now if you look at this, you can look at it in terms of point by point or whatever, but the main point here that I want to show is taking the derivative with respect to x3 of a function where x3 is a constant makes the whole thing 0. I don't know if that makes sense. Let me explain it again with this one. So taking, okay, so for example in this case, f3 is not kept constant here because we're taking with respect to f3. So that would just probably be whatever the derivative of f3 would be, the partial differentiation, that would be valid. So not going to 0, in other words. But when this derivative or differential gets multiplied in, that will be taken with respect to x1, and whatever that derivative is going to go to 0 anyway. So that becomes 0. The same idea goes for this. Taking the partial derivative with respect to x3 of f1 is going to be 0 because everything else is kept constant except x1, but since x1 is not in respect to this differential, it's also going to go to 0. Same applies here. And ultimately, when you've taken this derivative with respect to x2 inside there, it's also going to be 0. And the same goes for this. And this is equivalent to 0, which is exactly what needed to be proved here.